Natural language processing, often abbreviated as NLP, is the field of artificial intelligence that focuses on enabling machines to understand, interpret, and generate human language. It sits at the intersection of computer science, linguistics, and machine learning, and it has become one of the most influential areas of AI because language is the primary medium through which humans communicate knowledge, ideas, and emotions. To appreciate NLP, it is useful to consider the challenges it addresses. Human language is ambiguous, context-dependent, and constantly evolving. Words can have multiple meanings, sentences can be structured in countless ways, and meaning often depends on cultural or situational context. NLP provides the computational tools to handle this complexity. At its core, NLP involves representing language in a form that computers can process. This begins with text preprocessing, where raw text is cleaned, tokenized, and transformed into units that algorithms can handle. Tokenization breaks text into words, subwords, or characters, depending on the model. Stop words may be removed, stemming or lemmatization may be applied to reduce words to their base forms, and text may be normalized to handle case or punctuation. These steps prepare language for computational analysis. Early NLP systems relied heavily on rule-based approaches, where linguists and engineers defined grammars and dictionaries. While these systems could handle structured tasks, they struggled with the variability of natural language. The shift to statistical methods allowed models to learn patterns from data rather than relying solely on handcrafted rules. One of the foundational ideas in statistical NLP is the distributional hypothesis, which states that words that occur in similar contexts tend to have similar meanings. This idea led to the development of word embeddings, where words are represented as vectors in a continuous space. Embeddings capture semantic relationships, allowing models to reason about similarity and analogy. For example, the vector difference between king and queen resembles the difference between man and woman. Embeddings transformed NLP by providing a way to represent meaning numerically, enabling machine learning algorithms to operate on language effectively. As NLP evolved, neural networks became central. Recurrent neural networks, and later LSTMs and GRUs, were designed to handle sequential data, making them suitable for language tasks. They could capture dependencies across words in a sentence, though they struggled with long-range dependencies. Attention mechanisms addressed this limitation by allowing models to focus selectively on relevant parts of the input. The transformer architecture, introduced in 2017, revolutionized NLP by relying entirely on attention. Transformers process all tokens simultaneously, using self-attention to capture relationships across the entire sequence. This parallelism makes them efficient and powerful, and it is the foundation of modern large language models. NLP tasks are diverse. At the simplest level, there is text classification, where models assign labels to text, such as spam detection or sentiment analysis. Named entity recognition identifies entities like people, organizations, or locations in text. Part of speech tagging assigns grammatical categories to words. Machine translation converts text from one language to another. Summarization condenses text into shorter versions while preserving meaning. Question-answering systems extract or generate answers from text. Dialogue systems and chatbots engage in interactive communication. Each of these tasks requires models to capture different aspects of language, from syntax to semantics to pragmatics. Training NLP models involves large datasets and specific objectives. Language modeling, where the model predicts the next word in a sequence, is a common pre-training objective. Masked language modeling, where words are hidden and the model must predict them, encourages bidirectional understanding. These objectives teach models general language competence, which can then be fine-tuned for specific tasks. Fine-tuning adapts pre-trained models to domains like law, medicine, or customer support, aligning them with specialized vocabularies and styles. Reinforcement learning from human feedback further aligns models with human preferences, ensuring that outputs are not only fluent but also helpful and safe. Evaluation in NLP is complex. Metrics like accuracy, precision, recall, and F1 score are used for classification tasks. Perplexity measures how well a language model predicts text. Blue and Rouge scores evaluate translation and summarization by comparing outputs to reference texts. Human evaluation remains essential, especially for tasks like dialogue, where quality is subjective. Robustness and generalization are critical, since models must handle diverse inputs without failing. Interpretability methods, such as attention visualization, provide insights into how models process language, though full transparency remains elusive. NLP also raises ethical and social questions. Because models learn from large datasets, they can inherit biases present in the data. If certain groups are underrepresented or misrepresented, models may produce biased outputs. Addressing this requires careful data curation, debiasing techniques, and fairness metrics. Safety is another concern, as models may generate harmful or misleading content. Governance and oversight are needed to ensure responsible deployment. Transparency about training data and alignment goals helps build trust. NLP is not just a technical field but one with profound societal implications. Applications of NLP are everywhere. Search engines rely on NLP to interpret queries and rank results. Virtual assistants use NLP to understand commands and provide responses. Translation systems break down language barriers. Summarization tools help manage information overload. Customer support chatbots provide scalable interaction. Code generation models assist programmers. Medical NLP systems analyze clinical notes. Legal NLP systems process contracts. The versatility of NLP makes it a cornerstone of modern AI applications. Looking ahead, NLP is moving toward multimodality, where models integrate text with images, audio, and video. This allows richer understanding and generation, such as captioning images or transcribing speech. Retrieval augmented generation combines language models with external knowledge bases, improving factual accuracy. Continual learning aims to keep models up to date with new information. Personalized NLP seeks to adapt models to individual users, though this raises privacy concerns. Hybrid approaches combine statistical learning with symbolic reasoning, bridging data-driven methods with structured knowledge. These directions suggest that NLP will continue to evolve, becoming more powerful, adaptive, and integrated into everyday life. In summary, natural language processing is the field that enables machines to work with human language. It involves representing text numerically, training models to capture patterns, and applying them to tasks like classification, translation, summarization, and dialogue. It has evolved from rule-based systems to statistical methods to neural networks and transformers. It relies on embeddings, attention, and large-scale training. It raises challenges of evaluation, bias, and safety. It powers applications across industries and continues to expand into multimodal and hybrid systems. NLP is both a technical discipline and a societal force, shaping how humans and machines interact through language. Understanding its basics is essential for anyone who wants to become an AI expert, because language is the key to intelligence, and NLP is the key to making language computational.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.